The types of dielectrics which which has been classified, means the dielectrics have been classified based on their crystal structure, because the polarization of the dielectric material inside a crystal, inside a dielectric material, inside a material is depends on electric field, means what kind, how much amount of electric field is applied on it, as well as it also depends on the structure of the crystal. So based on the based on the structure of the crystal, the dielectrics have been classified into, see, this is what the tree diagram of classification of these dielectric materials. The dielectric materials have been classified into three types here. Those are piezoelectric materials, pyroelectric materials, and ferroelectric materials. So these piezo, pyro, ferroelectric materials, what do you mean by these materials? In the sense, normally we have, based on the structures of the crystals, there are 32 crystal classes are there. In your earlier classes in chemistry especially, you have gone through the Brevis lattices. Brevis lattices, there are 14 Brevis lattices are there. So to define that Brevis lattices, means to describe those Brevis lattices, we have gone through the topic called as unit cell. A unit cell is going to be having, it's the smallest part of the crystal which we repeated itself in 3 dimensions or in the space. We will get the entire crystal structure. That is known as your unit cell. Now that unit cell has three primitives, nothing but three sides, A, B, C, and three axes, crystallographic axis. Those are OX axis, OY axis, and OZ axis. In between them, in between those crystallographic axes, there exists interfacial angles, alpha, beta, gamma. So for different values of alpha, beta, gamma, A, B, C, you are going to be getting approximately 237 crystal systems, shapes, crystal shapes. Those crystal shapes, based on their symmetries, based on their similarities, the people have been classified into 32 crystal classes. Among these 32 crystal classes, 11 are centrosymmetric and 21 classes are non-centrosymmetric. Non-centrosymmetric. You know, symmetric structures. By folding a paper, a square paper into 4 times, we'll get 4-fold symmetry, 2-fold symmetry, 3-fold symmetry. If it is possible, that symmetry is possible with the at the center or a line passing through the center, then they are called as centrosymmetric crystals, crystalline structures, or else they are called as non-centrosymmetric crystalline structures. These are 20 non-centrosymmetric crystalline structures have been named as piezoelectric materials. Why? Because due to that non-centrosymmetric nature, if you apply some pressure on them, it means mechanical force on them, they possesses electricity. Electric charges are going to be developed. You know that the separation of charges will take place when you apply electric field in dielectric materials. Similarly, when you apply electric field on that, sorry, when you apply some mechanical force on that, there exists some electricity in these materials. Those are called as piezoelectric materials. These piezoelectric materials which are possessing unique polar axis, are called as pyroelectric materials. I think it is very clear. The piezoelectric materials which are exhibiting unique polar axis. What do you mean by polar axis? It means a single direction of polarization will take place in these materials. Single direction of polarization. Such materials are called as unique, exhibiting unique polar axis. Those are called as pyroelectric materials. And the remaining 10 classes are going to be non-pyroelectric materials. We are not bothering about them. These 10 classes of pyroelectric materials which are exhibiting hysteresis curve, we will see that what all these are exactly, which are exhibiting hysteresis curve are called as ferroelectric materials. Ferroelectric materials, you see that a ferroelectric material must be a pyroelectric material, it must be a piezoelectric material, but vice versa is not true. You know that piezoelectric material may or may not be a pyroelectric material, or a pyroelectric material may or may not be a ferroelectric material. That's what the classification of the dielectric materials based on their crystalline structures. Basically, there are three types: piezoelectric materials, pyroelectric materials, and ferroelectric materials. See, what do you mean by piezo? Piezo stands for pressure. What do you mean by pyro? Pyro stands for fire, or else we can call temperature. Ferro stands for, ferromagnetic materials. What kind of nature they exhibit? Same kind is going to be possible with this ferroelectric materials also. Is so that here we'll go through each and every type of materials now. Each and every type of materials. So again, we are going to be describing in this slide here. One is type of dielectric materials. That is 32 classes are going to be there. Majorly, we have 32 crystal classes. Out of these 32 crystal classes, 20 classes are non-centrosymmetric materials. They are called as piezoelectrics, and they exhibit piezoelectric effect. And the example for piezoelectric effect is quartz alpha. Quartz alpha is a piezoelectric material, and among these 20 classes, 10 are pyroelectric materials which exhibits unique polar axis, and these are responding for temperature, whereas your piezoelectric materials are responding for pressure. These pyroelectric materials are responding for change in the temperature. Aluminum nitride, zinc oxide are pyroelectric materials. Now, among these pyroelectric materials which are exhibiting hysteresis loop are called as ferroelectric materials. You may have a doubt. What do you mean by this hysteresis? We will see what is that exactly. Now, what are the examples for your ferroelectric materials in the sense? Barium titanate and lead zirconate and ilmenite family, including lithium niobate, tantalate, are ferroelectric materials. Lithium tantalate, lithium niobate. These are the examples for your ferroelectric materials. These dielectric materials are where we have the nature. By the nature, we can get some of the dielectric materials, and artificially also we can manufacture these dielectric materials. The artificially made dielectric materials are, excuse me, named as ceramics, whereas the natural dielectric materials are named as normal dielectric materials. So this is what the types of dielectric materials that we have. Now, once again, we will go through the what do you mean by piezoelectric materials? What do you mean by piezoelectricity? And what are the examples? What are the what are the properties that are going to be exhibited by piezoelectric materials, and also pyroelectric materials as well as ferroelectric materials? These are the things we are going to be learning in detail in this class. Now we'll go through the piezoelectric materials. As I already told that Piezo stands for pressure. What does it means? When you are applying pressure on these materials, on dielectric materials, there exists some polarization inside the materials. As a result, you are going to be getting electricity. Electricity means mechanical energy we can convert into electrical energy by these piezoelectric materials. See, very simple here. The piezoelectric materials are the crystals which are exhibiting non-centrosymmetric crystals. Due to this non-centrosymmetric nature only, they are going to be polarizing when you are applying electric magnetic mechanical force on them. So these are the piezoelectric materials are going to be exhibiting two types of effects here, two types of phenomena we can observe in these materials. One is piezoelectric effect, and the another one is pyroelectric effect. Pyroelectric effect. Sorry, inverse piezoelectric effect. So what do you mean by piezoelectric effect? It means in this effect, this effect translates the creation of electrical charges during the application of mechanical constraint on the piezoelectric material. Very simple. When you are applying a mechanical force on that, electrical charges are going to be created. This was explained by Curie on that material, CURAT. So this is called as piezoelectric effect, and again we'll read about this piezoelectric effect, learn about this piezoelectric effect. And reverse are also possible. Reverse in the sense, when you apply electric field on the piezoelectric material or any dielectric material, you may get mechanical energy. You may get mechanical energy means inversion of your piezoelectric effect is also possible. That also given by Lippmann here. So the induced appearance of mechanical strain in the material during the application of an electric field, this is called as your inverse piezoelectric effect, that we will see now. So see, when you are going through the piezoelectric effect, the piezoelectric effect linearly links a mechanical variable to an electrical variable. See what we are doing there. We are taking a dielectric material, we are pressurizing it, means we are applying some pressure on that. As a result, electrical energy is going to be generated. You please see the diagram here. In this diagram, what you are able to observe, you take a piezoelectric material, apply in between, apply pressure on that. So when you connect, if you connect it to a bulb is going to be glowing there. So what does it mean? Electrons are produced through these electrodes and passing through this wire, and this is going to be illuminating this bulb. So that how it is going to be possible in the sense due to the piezoelectric effect only. The process by which a dielectric material acquires electric polarization due to the external mechanical pressure. The process by which the electric material acquires electric polarization due to external mechanical pressure is known as piezoelectric effect. It linearly links the mechanical variable to an electrical variable. We will see the application where we use these things. I'll give you a simple example or simple what we call application here. See, you people have seen that when in kids' shoes, we can use this kind of dielectric materials. As a result, lights can glow when they are moving here and there. So when they are applying, when they are tapping their foot, the lights are going to be glowing there because of this piezoelectric effect only. That we will see that in future also in detail. So now this is going to be discovered by Curie brothers in 1880. You please see that it is in 1880, not in 19, right? It translates the creation of electrical charges during the application of mechanical constraint on the piezoelectric material. That's what we have discussed already. And then now inverse piezoelectric effect. You know that the inverse of piezoelectric effect. In piezoelectric effect, what you have done? You applied the pressure, you got the electricity. Now you apply the electric field, you'll get the pressure. Means mechanical strain is going to be there we can observe here when you apply electric field on that. You see that the diagram here. Externally, VDC is the external source we are using here. You are applying the pressure on that, on a piezoelectric material. As a result, we can get some kind of ultrasonic waves. That is one application of your inverse piezoelectric effect, production of ultrasonic waves, and so many. Right. So induced the appearance of a mechanical strain in the material during the application of electric field. Simply, when you are applying electric field, mechanical strain is going to be there. That we are calling it as inverse piezoelectric effect. Lippmann suggested this effect, and what he has used, quartz. Quartz is a non-pyroelectric piezoelectric material. It's not pyroelectric material, but it is a piezoelectric material. It is also exhibit this inverse piezoelectric effect. That's what the nature of your inverse piezoelectric effect. And the electricity which is produced in these two cases is known as piezoelectricity. Where we use the applications of your piezoelectric side is this. In automotives, we use airbag sensors. Airbag sensors. How these airbag sensors in cars are going to be possible in the sense, when a pressure is applied on them, means when a car is going to be met with an accident, a large amount of force is acting on the on these airbag sensor. As a result, the bags are going to be opening there. It means this kind of application that we have with this. And airflow sensors, audible alarms, fuel atomisers, keyless door entry, seat belt buzzers, knock sensors. All these are the applications of your piezoelectric materials. Means these are going to be responding there when you are applying some pressure on them. Electrically means electrical signal they are going to be generating, and they are sending towards the sensor. Electrical sensor is going to be sensing them, means your piezoelectric material acting as a sensor, and which is in automation of any tool or any material or anything, we are going to be using this. And computer disk drives, inkjet printers, we use these piezoelectric materials. And cigarette lighteners, you know that, depth finders, fish finders, humidifiers, jewelry cleaners, musical instruments, speakers, telephones. We use, in all these cases, we use piezoelectric material. I'll give you in telephones where we use a mic. If you have a mobile, in the sense you have a mic piece is going to be, when you are speaking in front of your mic, what happens, the mechanical waves, sound waves are going to be generated here. These sound waves are nothing but your mechanical waves which are going to be incidenting on those dielectric materials, and they are converted into electrical energy. Piezoelectric effect will take place. And coming to your speakers, in speakers, electrical signals are coming into that speakers, the electric materials are getting vibrated. As a result, you are going to be getting these sound waves. So this is what the application of your piezoelectric materials in your mobiles. And even in medical field also we can use them. And also especially in ultrasonic waves are going to be produced by these piezoelectric materials. And we use in sonars, radars, we use mostly ultrasonic waves. There we use this in military applications also, we use this piezoelectric materials. So this is what the application of your piezoelectric materials. And some of these applications also extended towards the other classification, other type of dielectric materials also, because a piezoelectric material may or may not be a pyro or ferroelectric material. That's why some of the applications also extended towards the another kind of classification of your dielectric materials. So this is what we have done till now. What is piezoelectric materials? What is piezoelectricity? And what is piezoelectric effect? And what is inverse piezoelectric effect? And what are the applications of piezoelectric materials? And what are the examples for these piezoelectric materials, in the sense Rochelli salt, Rochelli salt, and your quartz crystal, and also barium titanate, and also lithium niobate, lithium tantalate, All these are the examples of your piezoelectric materials. So, and next we are going to be another kind of dielectric materials called as pyroelectric materials. Pyro stands for temperature, means when when you heat these materials, dielectric materials, you are going to be getting, means the dielectric materials are responding for temperature, means when they are getting heated or cooled, pyroelectricity is going to be produced in those materials. Pyroelectricity can be described as the ability of certain materials to generate a temporary voltage when they are heated or cooled. So there exists a temporary voltage when they are getting heated and cooled. So that's why we can say that when temperature changes, the appearance and disappearance of charges on the extremities of the crystal will take place. That it means as the temperature is getting changing, you are going to be getting the polarization of the crystal, and sometimes disappearance of the crystal. Polarization inside the crystal will take place. I'll give you a simple example here. You know, thermostats. In thermostats are majorly pyroelectric materials. See, when the temperature is increasing, they are getting expanded. When the temperature is decreasing, they are getting contracted there. As a result, you are going to be getting, fridge is getting, sometimes it is in on and sometimes it is in stable, I means idle. So that's what the nature of your pyroelectric materials. And this pyroelectric crystals has spontaneous polarization in a given crystallographic direction. So the pyroelectric materials already they have themselves, they have some kind of polarization without any external sources. This is what your polar dielectrics. Polar dielectric materials have spontaneous polarization. If you increase the polarization there, automatically dipolar polarization will take place. What happens there? Orientation of those polarization will take place. And sometimes if you decrease the temperature, they can disalign here, as so that the disturbance is created in the polarization of the material. So pyroelectric crystals has spontaneous polarization in a given crystallographic direction. A temperature change leads to a change in the thickness of the lattice, and therefore the dipole moment, hence the appearance of charges on the extremities of the dielectric. The dielectric is in the case of called pyroelectric or piezoelectric. Oftenly it is simply pyroelectric material. In a simple way, what happens when you are increasing the temperature or decreasing the temperature, in the sense the dipole moment of those polar dipoles is going to be changing. As a result, we are saying that the appearance of charges and disappearance of charges will take place inside the dielectric material. Hence they are called as pyroelectric materials. Like we'll go through the this topic in detail here again. The pyroelectricity is an ability of the material to generate an electric signal when it is subject to a thermal change. When you apply some temperature on that, pyroelectric materials are going to be generating some electric signals here. Very simple. If you use temperature sensors there, based on the now to do the thermal scanning, we are using the temperature sensors. There you are going to be using pyroelectricity to detect corona. The in aerodromes or else in shopping malls, they are doing thermal scanning. They are measuring your temperature, body temperature. So when the temperature is going to be incidenting, mean they are sending some electromagnetic waves onto you. As a result, as the temperature is going to be more, then obviously it shows the pyroelectric material is going to be showing that change in the electrical signal. As a result, you are going to be getting the pyro, means change in the pyroelectricity will take place. That shows you the temperature of your body. That is one of the application. You know that P is the polarization. The change in the polarization with respect to the temperature is known as pyroelectric coefficient lambda, which is very important while knowing about the pyroelectricity. Change in polarization results change in the external field, and hence change charges on the surfaces here. And what are the properties which are going to be exhibited by these pyroelectric materials? In the sense, they have unique polar axis, which means polarization is along at a certain direction. Polar axis may or may not be reversible. by reversing the direction of the applied field, and exhibits non-centrosymmetricity because they are piezoelectric effect, piezoelectric materials only. That's why they are also consequently they are also exhibits this kind of nature. And pyroelectric materials exhibits pyroelectricity when the temperature is greater than the Curie temperature, greater than the Curie temperature. That's what your pyroelectric materials. Curie temperature is the material where it is going to be changing into a paramagnetic material, or else a diamagnetic material is going to be converted into a ferromagnetic material, that we will see in the magnetic materials. See properties of magnetic materials. See applications. What are the applications that we have in the sense? We have pyrometers, highly sensitive thermometers, pyrometers in the sense, the last one, and the temperature sensors we can make, and infrared detectors also we can make here, and pyroelectric image tubes. We can make all these things using this pyroelectric materials. And the last one, that is nothing but your ferroelectricity or ferroelectric materials. The ferroelectric materials are the among these pyroelectric materials which are exhibits hysteresis loop are called as your ferroelectric materials. What do you mean by hysteresis loop? You are able to see this hysteresis loop on this right hand side. But even though I will go through this one in the next slide about your hysteresis loop, you see this when you are consider a dielectric material placed in an electric field, apply some electric field on that. As a result, the the polarization inside the material is also increasing. As you increase the strength of the electric field here, even the polarization is also increasing. At a certain point, at a certain point, it reaches the saturation in its polarization. Further increment in the electric field, there is no increment in the polarization will takes place. Now, after reaching the saturation in its polarization, now apply the electric field in the opposite direction. Apply the electric field in negative x direction. As a result, polarization vector will not move along the same direction. It will move along, it will trace another path here, and even in the absence of some electric field, it shows some electricity, means polarization inside the material, that we are calling as retentivity or remanence. Remanence or remaining polarization inside the material even in the absence of some electric field. And further increment in the electric field in the opposite direction, at a particular field, the remnant polarization becomes zero. The remnant polarization becomes zero. That is what you are calling as coercive field. The field which is used to kill this retentivity is known as coercive field. And after further increment in this electric field in the opposite direction, the same scenario that you have initially observed is going to be taking place here, and further increment in it, you are going to be obtaining a loop called as hysteresis curve. So the materials which are exhibiting ferroelectric materials, in the sense, the pyroelectric materials which are exhibiting this kind of curve when they are placing in an electric field are called as your ferroelectric materials. The ferroelectric materials are nothing but your pyroelectric materials. They are also nothing but your piezoelectric materials. What are the examples for your ferroelectric materials? In the sense, lithium niobate, ammonium, dihydrogen phosphate, and barium titanate, Rochelle salt are the examples for your ferroelectric materials. And what are the applications with this ferroelectric materials? In the sense, pressure transducers we can make, ultrasonic transducers we can make. You may ask, what do you mean by transducers? We'll see that later. RAMs as a memory storage device, we can use RAMs. There we use this only. Ultrasonic waves generation, we can use here. And then used in delay lines applications, delay line communication devices here, and also we can use them in producing ultrasonic waves. So these are the normal applications of your piezoelectric materials. So I will go through that. One more slide here. Examples of your piezoelectric material. Every piezoelectric material may or may not be a pyroelectric material. or you using this what we call a Venn diagram we are showing here. A piezoelectric material may or may not be a pyro. It may or may not be a ferroelectric material. I've given the examples also here. A quartz is piezoelectric only, not pyroelectric material. And ZNO CDS. These two are the piezo as well as pyroelectric material, but not ferroelectric material. PZD, PM, PT, and PV, polymer. All these are polymer materials. All these are going to be your ferromagnetic materials as well as pyroelectric materials as well as piezoelectric materials. So that's what your the basic classification of your magnetic dielectric materials. And also we will see this the first slide once again here. You please observe here, the piezoelectric materials are responding for pressure, pyroelectric materials are responding for fire, ferroelectric materials are responding for electric fields. So we use these piezo, pyro, and ferroelectric materials wherever is needed by using their properties here. Piezo are responding for mechanical applications, means mechanical pressure is going to be there. And pyro is going to be firing alarms we use there. Ferro is going to be electrical energy is going to be applied on them. This is what the types of dielectrics about classification of your dielectric materials. I think everybody understand this. Everybody understand this. Uh, yeah. Do you have